Let's continue now a little bit further aspect of shape, but also textures in images. And yeah, the usual list of literature and also the different modules that I've been using. And now we go into different aspects. Until now we looked at just individual objects and how we can characterize each object. Now we're going into something called distance and thickness maps, but also into a very different field called texture analysis. And how can we measure the size of different complicated objects is the good question. And also in some cases, the size distribution may also have an impact on diffusion and other local processes in the object. So we want to look into how to characterize this in a little bit different way, and also how the shape behaves if they are growing and how they grow. And the second part is if we have patterns, how we can quantify these patterns and use them for our analysis purpose. And first of all, the distance map is an image which represents distances in between objects in your image. It could be distance from the surface of an object or inside an object. It can also be relative to the center of the object, depending on how you define it. And again, we need to have some metrics. We have already talked about the 4 and 8 connected metrics, but now we are also going into using the Euclidean distance. And if you look at the city block distance, which is the 4 connected one, it can only go horizontally and vertically, and that gives us some distance. The checkerboard distance can also go diagonal from pixel to pixel, but it cannot do the exact point to point still, so it has to go first some horizontal in this case, and then does a lot of diagonal, and then finally doing the last horizontal. If you do the Euclidean distance, it's actually just computing the distance in Euclidean coordinates between 2 points, and then you get a different value. And as you can see, depending on which metric you're using, you have also different distances. And you may ask, why using this or that? And again, speed. Sometimes it's sufficient to use 4 connected neighborhood, and you can come across your calculation very fast. In other cases, you need the really precise measurement, and then you go for the Euclidean distance. So what does it look like? Here we create a little test image, just a dot, black and white, so from our segmentation. And if you compute a Euclidean distance map, this is very small, so let's make it a bit bigger, so you may see the numbers here. So outside the object we have only zeros because it's outside. And then the first row of pixels we have 1, and then in this first hidden pixel in the corner here it's 1.4, square root of 2. And if you go to this one, it has the shortest distance is the 2, and then yeah, you continue like this. And it's always the shortest Euclidean distance from this edge to a point. We can also compare the different ways of computing the distance transform. There are different algorithms. Some have developed to be a lot faster. And for example, here we have the exact Euclidean distance transform. Here as computed with a brute force algorithm. you get the same values, but you can see there is already a difference in computation time. And here is a kind of a smart local structure algorithm, which is called chamfer distance transform. It's somewhere between the 8 connected and the Euclidean distance transform. So it gives you a better approximation, but often in shorter time. This time it didn't do that much of a difference. So we have 10.2 microseconds here and 9.7 microseconds here. Didn't do much difference here, but there are cases when it really makes a big difference. And this is something we want to do also in 3D on large images, so it really goes into time. In particular, as to compute the Euclidean distance, you have to compute square roots, and they are expensive. And yeah, here we come to the why speed matters. In small images, you don't see much difference. You don't care. But if you come up to images that are over 2K cubed, then it starts getting important. And in particular, if we have multiple scans of the same, so then it really becomes an issue that it takes some time. Here we have a little extrapolation of execution times. So it's probably not completely fair, but anyway, here we have an image, 512 squared, and with just a circular object. Distance from here took 11 milliseconds. If we would extrapolate it to a volume of the more than 2K cubed, then it would take 0.16 hours. The brute force algorithm, which is not really what you should use, but it's nice for demonstrating how it works, can be used as ground truth or benchmarking reference. Then it takes almost 6 hours to compute a full volume. And the chamfer is here you start seeing the improvement, because this one takes a quarter of the time that it took for the exact transform. And you can see out at the perimeter, it's actually pretty good. But at some point, it starts getting this diamond shape when it's too far distances. So at some point, it's really less precise. But again, it may be sufficient for what you want to do, in particular for small objects. Computing a distance map is a lot of loops, in particular with the brute force algorithm. And in principle, what it does, it's computing the minimum distance to the background. And well, I'm not going into the details of this algorithm. You can do it, look at it if you like. One thing is just that, let's see, yeah. So the distance here is in principle that you compute this Pythagoras for the distance between the two different positions, and that is iterated many times. So one thing it's iterating over the whole image, and the other thing is iterating around the local neighborhood. Seeing what it looks like, so let's create a little test image for the distance transform, and let's see, there he comes. And here we can run. The initialization is that you have first zeros and the largest value you can have, and then it tries to optimize this as much as possible. And you can see that in the iterations, it goes also like a kind of a region growing effect, that it goes from the outside and then shrinking into the middle. There are, of course, many different algorithms for doing this, also doing it in parallel, and so on. So, as this is a very central topic in many algorithms to have this distance map. And yeah, you can do different metrics. Before we have the Euclidean distance. If you do the city block, then you take the absolute difference between two positions and run the same thing. So here you see the absolute, or actually the sum of the absolute distance. So how many steps in X and how many steps in Y, and that is what you're iterating through your image. And if we animate this one, you can see that you get now like rings of a distance going inwards, and you don't have the fractions that you had in the Euclidean distance. Yeah, so this is a cheaper operation to compute, and that's why it's still considered. And there are a couple of things that you have to think about. One is that when you compute the distance map, you have to think about what size your pixels are. If you have cubic isotropic voxels, everything is fine. But I got the question early in these lectures, what happens if you have thicker slices? So you have, for example, 1 micron by 1 micron by 10 microns. Then you have to adjust your algorithm in a way that it actually takes care of this anisotropy in the voxels. Otherwise, you will have very misleading results in your distance map. And well, that was a bit. And then, of course, you can compute distance map in two different ways. You can do foreground to background or background to foreground. And here we see what it would look like. So what we have done until now is always foreground to background, and then you get into the objects. But it could actually be that you are more interested in seeing the distance between objects instead. And then you flip the image and the image segmentation, so you have the whole background is white instead of the objects, and then you can compute out in the object like this. So again, depending on what you want to achieve, you sometimes compute the distance between the objects and sometimes the distance within the object. And let's have a little demo what can happen or how you can use this also to better quantify your image data. If you have two objects, in principle two ellipses, and start growing them, dilating them. And in one case, you compute the label it and compute the average area. And the other case, you compute only the distance map and want to see what effect you got. And this runs. Hey, come on. So we start with the single dots, and then we let them grow. And you can see in this average area, you can see, or average distance, you can see that it doesn't grow much with the distance map. But if you do the component labeling, you see that all of a sudden the area just spikes away. And what's happening is that the objects here, they merge, and then all of a sudden you only have one single object and you get the area of the whole object. If you compute the average distance, you don't have much of this effect. Okay, you're growing a little bit, so that gives you also a larger distance, but you don't get this step behavior as you did when you have component labeling and computing the area. So this is a way to, in some cases, compute a more robust object size estimate. And then we have some real images. We can look at this cell bone example where we have the mask. And now I use the mask to compute the distance transform in the foreground in these marked objects, or the distance map of the background, and then you can see here what you get is in principle the distance between each object, and the value here is pretty much higher than the value here, and that's because these objects are much closer than in this area. So with that you can in principle quantify how far apart each object is. We are going to use the distance map also next week very much. One part will be used to quantify really how large activity area does each object have. And then we will do some quantification, which we will even use in 2 weeks. No, 3 weeks, because there is Easter between. Looking at the cortex, just taking the mask from it, computing the distance transform, we can see that we have a thicker part here than we have down here. It can be used for the analysis. Not so much to say about it actually. If we look in the closer, we can even do a histogram of the distances, but it's kind of a bit awkward information to look at, and I'm soon going to show you something that tells more about the thickness of the object, because here we only know that this single pixel here is at the thickest place, but there's only one pixel telling that it has a very large large area. Another way we can use the distance transform is to compute averages as function of the distance. In this case, it's soil aggregate, so actually just a little soil crumb. And we want to look at the porosity and the grade level distribution. And with that, we computed the distance map for the whole object or the whole image. And then we took different shells or small segments and computed the average intensity and porosity and some other metrics from that. And another example is here we have little mini soil sample where we have a surface here, and we want to know how the porosity changes in the vertical direction. And there is actually a full notebook demonstrating all the steps how to do this. But what we have is let's start just computing the distance map from the surface here down into the object, and then we can compute the image intensity at different depth of from the surface. So I actually plotted the depth distance from the surface in this direction, and then gray level intensity here. And then we can see that there is a lower intensity at the top, which indicates that it may be more porous or drier or something. And then when it comes down, it settles down to some constant gray level. So I said in the cortex image that we only had one pixel to represent the fattest place, and an alternative to do this analysis is to use the thickness map, which represent where the pixel values in the image represent the radius of the largest sphere you can put in that area. And as a difference, you can see here is the distance map. You get a very thin line with the largest distance between the objects, and when you do the pore size map or thickness map, you get more blobby regions because they have larger volume that they can support. This is used a lot in porous media analysis, where you want to really know how big are the throats in your porous medium. It could be sand packing, could be bubble analysis in some cases, and so on. And here we have some different maps from an example that we did. This was used later also in simulations to follow how large, how the water is flowing through these media. And implementation is, in principle, you have to do first a distance map, and then you go backwards. So you take the largest radius, put on a sphere or a disk in the image on that place, and then you do that all over the image, and that iterates a couple of times until you have filled the whole pore space or the whole object with these sphere objects, and then you get this gradual change between over the image. So in this case, you have a very large blob in the middle, which means that we have large spheres, and then it's towards the edges where you have tiny details. The pore size, the spheres are getting smaller and smaller. As I said before, in this area here, we have a very large value because there are large distances. So that's also represented by a large intensity in here. And if you compare the thickness distributions in the foreground, then you can see the distance map and the thickness map. The distance map has a very high representation for small values, close to the edge. And the thickness map really clusters around where you have the large volume of large distance. And in the background, you can also see that you have the distance map has a tendency towards the low values, whereas the thickness map again clusters to some bigger clusters, and there is a huge one here apparently. So that can be helping you to identify where you have large regions, or if you have different types of regions in your image. But that is something we are going to talk about next week as well. In 3D, you can do it. Until now, we have only looked at 2D images, but of course, you have distances in 3D as well. So the principle is easy to step up in higher dimensions. And then it's just a question of more computational efforts to compute it. So here is an example of a 3D image loaded, but we now look just at axial slices. It's some bubble, I think it's some bubble material. And you can see in one direction, they are pretty isotropic, so almost round discs. Whereas in the vertical case, you can see that they are more ellipsoids that we are talking about. It can be rendered in a nice way using, for example, a surface mesh. Sometimes we do surface rendering rather. The surface mesh is something you can use also when you compute finite element simulations, because then you can put boundary conditions and forces on and let them propagate through this mesh. And that can of course also be rendered and visualized, so we can rotate it if we want. So for 3D, we often need to have some way of looking at different renderings to get an idea what the data looks like. So there we have the 3D tools to our help. If you compute the distance transform in this object, we can see that in the axial slices, we have more or less the same values, but at some places we have a little bit larger, which would be strange if you look at it in 2D. And the reason is that we have these elongated objects in the depth direction. Yeah, and then we can also look at thickness maps, and here you have nice bubbles telling where you have the large thicknesses, and that can give you a little bit of information also on how the bubble distribution is in the material. Yeah, the 3D thickness map we can just skip. And another way, 3D is always hard to visualize, so another way would be to also to do projections in different directions. In this case, it's a max projection, just to identify where we have the maximum bubbles located. Another projection is just taking the sum, but I think it's more intuitive to see these larger objects if you do the max projection, and you can see here from different directions. And otherwise, we can again look at the slices. We see that some bubbles are large, other ones not. And yeah, so we can compute again the region properties, for example, measuring what is the average intensity in each of these objects, or something like that. Let's look at the surface area now. And the surface area is something that can be tricky to handle because if we apply different thresholds, different erosions, dilations, or opening closings, it will actually affect the surface area quite a lot. And oh, now I'm a little bit lost in the order, it appears. Well, anyway, we can look at also at surfaces with the help of meshes. We saw this mesh rendering before. And this is a way to do analysis of objects or visualize them. And can also be used for deformation analysis. If you put some force here, you can see how things are bending and deforming. And this is a type of analysis that I'm not going into so much detail into how it's done. But the algorithm that is used in one way to identify these edges is called margin cubes. It's a pretty nice concept. You have a little cube, 2 by 2 by 2 pixels, and just by looking at the configuration, if a pixel is inside or outside of this configuration, you get surface elements, and that can be done very quickly because you can actually relate these 8 pixels into a lookup table, and then it can be easily translated into surface or triangle elements and triangles. But problem is, again, as I showed before, that voxels are poor approximations of a surface, and if you have very small objects, they are not really spherical, or the surface is not very well represented, and you need some certain size at least to be able to represent a surface well. One thing you can do from the surface analysis is computing the curvature, which is in principle 1 over the radius of the largest sphere you can draw on a local plate. And that gives you an idea how detailed, or the detail of the surface. And there, with the help of it, you can also compute the surface normal. And then you can get this hedgehog-like visualizations telling which directions. And the surface normal is something that is also used when you do renderings. Doing this visualization, want to see reflections and how it behaves. So how the light is reflected from the object can be told by this. And yeah, in 3D, you not only have one direction, but you can have several directions. So you have a minimum and maximum curvature at the local position. So you have 2 principal curvatures to look at. And then, depending on what you want to show, you can show also the mean curvature or the Gaussian curvature. And it depends also on, again, what you want to show. And if you have plane for the Gaussian curvature, it's a 0, which is also pretty nice because then you can reduce a lot of information. That can be visualized or plotted in our bubble example. It's not so clear here maybe, but you can see that there are locally small fluctuations in the curvature of this object. Let's see here. No, yeah. Let's skip that one and continue on. Let's see. Let's go on with the texture analysis instead. So this is a completely different topic from the characterization of images. The world is full of different patterns everywhere. We have natural patterns, we have man-made patterns, but here is a little collection of different patterns that you can see out there. You can have leaves, you can have wood structures, you can have stones, you can have water, ends, etc., etc. And these patterns can, in some cases, also represent relevant regions in your data. And for that, we have very many ways of analyzing these textures. But in principle, what they are spatial patterns. And we need to do some analysis to get them. The problem is we need to use at least some minimal area to cover or to actually percept this pattern. You can't take a single pixel anymore, but you need to take a little bit larger area, which is large enough to get a statistical relevant representation of this. And therefore, the resolution of texture analysis will suffer. There are different ways of doing it. You can use statistical methods, you can use frequency-based, you can use also different model-based, morphological, edge-based, and so on to identify these structures. I'm right now mainly going towards the statistical one, where we look at these different patterns. In principle, very strict black and white patterns. Here is some kind of disk pattern, smoothest versions of it, and a tilted pattern as well. And what we want to look at is the gray level co-occurrence matrix, which is honestly a little beast to handle, because you have to compute the relation of first of all, intensity differences and position differences. So what this is doing is it takes one pixel, looks certain pixels away, and then it starts looking at how many do you have pixels in this area do you have which have the same difference in gray level. And that in the end results in some kind of 4-dimensional representation. And it's a little bit hard to get it to understand what it's actually doing. And then it's this one is just the sums, so it's often normalized to represent probabilities instead, to be easier to compare with other patterns. And here I ran it on the different patterns, have different positions and different distances, and I have, what was E now? That's the energy, and here is some D metric, and the theta is the orientation, local orientation, because you can also not only looking at distances, but you can take rotation and radius instead if you want to do that. So there are different ways of quantifying these matrices. In this case of our different test patterns, we want to test 4 different levels and 15 distances and 15 directions. And already this gives us quite a lot of information to work with. And when that is, so we have our different patterns here, and the co-occurrence matrix looks pretty strange here. But what we have is, in this case, in these three cases, we only have bi-level images, so we only have one row here, because the rows, they represent how many levels we work with, and because of that, we only have one row. And when we have more gray levels, then we go into several rows. That one is only also bi-level, so it's only a single row. And then we can look at the average values of these co-occurrences, and we see hopefully see some patterns in this. One way we can do is we can just look at some correlation, looking at the mean difference between two values instead of all these pairs. That reduces the information a bit. And let's see, that one shouldn't be shown. In principle, we can try applying these metrics using a microscope image from a sea urchin, and it looks something like this. I did some, call it layman segmentation as a mask, what I would see as changes in this texture. We have the core piece, which is here orange. Then there is some transition region, one region here with larger walls, and then you have the thin wall region out here. So, and here was also some field, I thought, when I marked it up. So this would be my mask, what I would expect. And if I overlay it on the whole thing, it looks something like this. So I use these gray level co-occurrence matrix to analyze it with the help of some metrics that can be extracted. First of all, the workflow would be first loading the images. We got some measured image and annotated mask. And the next step is to reduce the image into tiles, because we need some degree of coarseness to get our statistics. And then compute some feature vectors, maybe something else, and we could compute the co-location matrix and extract properties from that and analyze histograms, and finally do some clustering on this data. And first step is tiling the image. So I'm creating these tiles. I think I choose n equal 90. So and then I get all these little tiles, and each tile will be analyzed individually afterwards. Now you can see that there is some uncertainty. Also, if you compare with the mask that I showed before, that here it would be quite obvious, but in these edge cases, it could be less clear what we are working with. And now we compute the gray level co-location properties. I look at contrast, dissimilarity, homogeneity, some correlation, and ASM, and which is in principle some energy related parameter. And then we compute all these features and store them in a dictionary for the comparison, which has a lot of code. I'm not going to go stepwise, but what we get from this analysis is we have the original image, the regions that I identified. Then we have the contrast image, the similarity, and it looks like just a mess of tiled pixels. Maybe the energy image has at least a darker region down here. And now we want to look at a clustering of this. Here is just a table of all the pixels. And if we try to do a clustering with k-means and 5 classes, this one didn't came out very well. There's just a lot of strange classifications, so something is wrong here. And let's look at the statistics. So now we can use this map where we have each of the parameters that we're working with plotted against each other in bivariate scatter plots. The color coding is from my original image, from my original classifications, just to have an idea where things would belong to each other. The only thing that is more or less consistent among all of them is that we have a blob in the blue here. And I have to actually go back and see what the blue is, but it looks like that one is, it's probably the background. And then the other classes, they are very much overlapping. So it's not a very easy task to find a good metric here. Probably would need to do some better details, but yeah, the blue was the background. So looking at all these, we can see that in this region, the red is pretty clear, but then it mixes with the orange, and the orange mixes with the green, and so on. Looking at only the mean intensity and standard deviation, we can see that the red ones, they are a pretty nice cluster, and the background is also a pretty nice cluster. So those two should be easy to separate. The green, yeah, that could be a cluster, but the purple and the orange, they are in the overlapping zones, so it will be harder to grasp those. Given that, let's try instead with the 3-class segmentation and see what comes out. The clustering with k-means 3 on these two parameters gives us actually a quite reasonable separation between different regions. So I was maybe a bit too ambitious when I said 5 different classes with this texture. This is just a toy example that I played with. And probably with some more creative work, you can get closer to the regions than I did, or choosing a different method at all. But these features, they can produce, at least in some texture context, can produce pretty good results. Yeah, I could also play with improving. One idea I played with was also normalizing the vectors, because they are not, they are pretty wide span, so maybe normalizing could also help. But the normalization didn't come out well. So that brings us to the end of today's lecture. So I've been talking about first labeling, component labeling, and different metrics that we can compute on these objects. Then in the second part, I looked at distance map, surface descriptions, a little bit on visualizing 3D data, and now the last part, looking at textures as a way to identify regions in your data. And next week, I'm going to talk about Voronoi diagrams, which is actually an extension of using the distance map to identify how clustered objects are. And the other one is skeletons, minimizing the objects to the minimal structure, and also an alternative way of doing the component labeling. And well, that was the end of today.